Okay, for this screencast, what we're going to do is we're going to go over the application of differential equations using eigenvalues and eigenvectors. So let's say we have a differential equation, and I'm going to assume we have y double dot plus 2 times y dot plus 4 times y equals 0. Now typically what we've done in the past is we say y of n plus 1 equals y of n plus y dot of n times delta t, and then we said y dot of n plus 1 equals y dot of n plus y double dot times delta t, and then we said that y double dot is 2 times y dot of n plus 4 times y of n. And actually I think these are negatives. Now that's all well and good, but instead what I'm going to do is I'm actually going to write this in matrix form, and I'm going to say that my vector z of n plus 1 is equal to 1 delta t negative 4, and here let me actually write this in a better notation here. So I'm going to take this equation here and I'm going to substitute in y double dot like this, put it in there, and then I'm going to take this equation up here and I'm going to write this in matrix notation. So I'm going to say 1 delta t times y of n, y dot of n, and I'm going to put a semicolon here to denote that the second vector is a column vector. And now I'm going to do the same thing down here. So what I get is y dot of n plus 1 is negative 4 times delta t, and then I'm going to get 1 minus 2 times delta t times y of n, y dot of n. And what that allows me to do is now I can say, okay, let z equal y and y dot, and then I can say z of n plus 1 equals 1 delta t semicolon negative 4 times delta t 1 minus 2 times delta t times z of n, right? So then I can say, okay, well, what I'm going to do is I'm actually going to let my A matrix, so I'm going to say delta t equals 1, and I'm going to say my A matrix is 1 delta t, negative 4 times delta t, 1 minus 2 times delta t. And so that's just a matrix. Now what that allows me to do is now I can actually say that here I have z of n, I can do my while loop, while t is less than, say, 10, z of n plus 1 is just a times z of n. And I have to initialize everything. Remember, I have to say n equals 1, I have to say z of 1, and now I have to give it initial conditions. So I'm going to say y0 and y dot 0. I'm going to do transpose, so let's say y0 is 2 and y dot 0 is 0. And then I need to do n equals n plus 1, and t of n plus 1 equals t of n plus delta t, and t of 1 equals 0, and then I can go ahead and compute everything that I'd like. Now there is an issue here. Z is now needs to be a column vector. So what I want is I want z of all rows and then the column, and then I want to do all rows and then the column, because I need to make it a matrix. And what's going to happen is let me show you. If I run this, let's do a clear, a CLC, and a close all. Let's see, it didn't like it, so I'm just going to say z, and it looks like it was okay. So now look, so the initial condition was 2, 0, and then it was 2, negative 8, negative 6, 0. So notice, like, this really reduced the equations to be something super, super simple. Now I'm going to use eigenvectors and eigenvalues, and I'm actually going to do v comma l equals eig of a, and I'm going to make sure that v is correct and l is correct. And notice I get some imaginary components, but it doesn't matter. If I do V times L times V transpose, I should get A. And let's see, I didn't get exactly what L is, so let's see what's going on real quick. Okay, so it turns out that when you get V and L, V transpose times V is not equal to identity, and V times V transpose is not equal to identity. And that's because V and L have imaginary components. So instead of doing A reconstructed equals V times L times V transpose, we actually need to do the inverse of V on the left. So what we'll get is we'll get A and then A reconstructed. And there we go. So now we have V times L inverse V. So what I'm going to do real fast is, before I show why I did that, I'm going to come down here and I'm going to say Y is Z of the first row, all columns. Y dot is Z of the second row, all columns. And I'm going to plot T comma Y. And so here is, oh, and let me make my time step 1. So here is my simulation, and it blows up, right? So let's investigate what happens. Well, we'll take a good look at this graph real quick. I'm going to replace A here with V times L times inverse of V. And we'll notice that I'll get the exact same thing here. Now, what happens is that you notice is that Z1 equals V times L times inverse of V times Z0. And then Z2 equals V times L times inverse of V times Z1. But V times L times inverse of V times Z1, Z1 is V times L times inverse of V times Z0. So if I simplify that, I get V times L times inverse of V times V is identity. So I get L times L times inverse of V times Z0. And if I reduce it down even more, I get V times L squared times inverse of V times Z0. And so what you notice is that ZK is V times L to the K power times inverse of V times Z0. Now what do you notice about L to the K? Well, if we look at L, this is L right now. It is 0 plus or minus 1.73 to the I. Well, if I do L squared, I get 3. And then if I do L cubed, I get -5. And then say, well, I did 45. I do 4, and then 5, and then 6, and then 7. What you notice is that the value of L squared keeps getting bigger and bigger and bigger, which means if the norm of my eigenvalues is greater than 1, L to the K goes to infinity. So what I need to do is I need to change delta T until, and what I'm going to do is I'm going to let this output, I need to change my delta T until my eigenvalues, the norm, is less than 1. So it looks like that's not good enough. That's not good enough. That's not good enough. Let's do 5. Let's do 4. Okay, so now let's look at this. Let's do the norm of L of 1, 1. Well, that's 0.9165, so that means that that's less than 1. So if we hit go and we plot this, our system is stable. If we go to 0.5, our system does this. Now what we can do is we can say, let's do the norm of L of 1, 1, and that's 1, which means that L to the 1,000th power is basically exactly the same because the norm is the same. So if I do 0.49, notice that my system will start to decrease, which means my Euler's method is now stable. Now if I go all the way down to 0.1, now look at my system. I've become stable. So the reason why eigenvalues is important in this case is because you need to make sure that these eigenvalues, the norm of them, is less than 0 so that you don't go to infinity. Otherwise, your entire system will blow up. All right, well, hopefully that's been helpful. Good luck.